You know, we often think the most elegant solution to a problem is also the best one, right? The cleanest, the most beautiful. But what if it's not? In the world of math and computer science, this isn't just some late-night thought. It's a real, high-stakes battle. Today, we're diving deep into a fascinating paradox at the very heart of mathematical proofs, this incredible trade-off between pure, beautiful logic and just raw brute force speed. All right, so here's the game plan. First, we're going to break down the core conflict. Then, we'll get into something called the computational scandal. Sounds dramatic, right? After that, we'll see how researchers are taming this explosion of complexity, look at a really clever middle ground solution, and wrap up with why any of this actually matters for, the future of everything. Okay, let's jump right in. The heart of this whole thing is a fundamental clash, a real battle between two totally different ways of proving something is true. So picture this. On one side, you've got proofs that use what are called cuts. The easiest way to think about these is that they're the clever, shortcut-taking proofs. They use lemmas, which are basically just saying, hey, we already proved this other thing, so we'll just use that result. They're powerful, and they can be dramatically shorter. Then, on the other side, you have the cut-free proofs. These are the purists. They're simple, elegant, and what we call analytic. Every single step has to follow directly from the step before it. No outside help, no shortcuts allowed. And that specific tool, that mechanism that lets you take these shortcuts, it's called the cut rule. It's really just a formal way for a proof to say, look, we already went through the trouble of proving this other statement, so let's just plug that result in right here and keep going. It's an incredible tool for making things more abstract and, of course, way more efficient. Okay, so here's the million-dollar question. What happens when you try to be a purist? What happens when you decide to get rid of all those clever shortcuts? Well, that's where things start to go completely off the rails. And I'm not just being dramatic here. Researchers in the field literally call these pure, cut-free systems extremely inefficient. The price you pay for that logical beauty, for that purity, it can be absolutely monstrous. So the process of taking a short, clever proof and stripping out all its shortcuts to make it pure is called cut elimination. And here's the kicker, the part that's just wild. This process very often causes an exponential blow-up in the proof size. We're talking about a proof that might have been just a few pages long, ballooning into something longer than the number of atoms in the known universe. No joke. And this is what they call the computational scandal. I mean, think about how inefficient that is. These pure, elegant systems are so slow they can't even keep pace with way simpler methods, like just building a basic truth table. You sacrifice all that efficiency for purity, and what you're left with is something that's just, well, practically useless for any really tough problems. So why? How do these proofs get so outrageously big? There has to be a reason, right? It can't just be random. And more importantly, if we can figure out why it's happening, maybe, just maybe, we can find a way to fix it. And it turns out there is a secret. The big reveal is this. These gigantic, universe-sized proofs, they aren't filled with brilliant, unique new steps. Not at all. They're actually filled with the most mind-numbing, insane repetition you can imagine. The same exact little piece of logic, a subproof, just gets repeated over and over and over again, sometimes an exponential number of times. Now that discovery is a total game changer, because as soon as you realize the problem is just massive repetition, the solution becomes obvious: compression, right? If you're just saying the same thing a billion times, we'll just say it once and point back to it. Find those identical subproofs, get rid of the duplicates, and shrink the whole thing down. It's such a beautifully simple idea for a problem that seems colossally complex. And this one idea has sparked a whole new direction in research. Scientists are now attacking this problem from every angle you can think of. They're building algorithms that automatically prune away the useless parts, designing new search procedures that avoid creating repetition in the first place. Really, they're trying everything to find that elusive, shortest path to a proof. Which brings us to a really interesting question. We've got these two extremes, right? The raw power of shortcuts on one side and the beautiful elegance of purity on the other. But do we really have to choose? Is there some kind of middle ground? To put it another way, can we have our cake and eat it too? Is there some way to get that incredible speed boost that comes from using lemmas without completely wrecking the beautiful logical structure of a pure analytic proof? Well, it turns out the answer is yes. Say hello to the analytic cut. It's a truly brilliant compromise. Basically, it's a watered-down version of the cut rule. It's a shortcut, but with strict rules. You're only allowed to use it in ways that don't break that core principle of analytic proofs, the idea that you're always working with pieces of the original puzzle. And what this clever compromise does is let the system get a major speed boost. It essentially mimics the power of those big shortcuts, but without making a total logical mess. It really is the best of both worlds. You get a big dose of efficiency while still holding on to that valuable logical purity. Okay, let's pull back for a second. We've been pretty deep in the weeds here with logic and proof theory. But why does any of this matter? Why should you or I care about this super abstract quest for the perfect proof?
Because at its heart, this whole field is tackling one of the biggest challenges in all of computer science, finding that perfect balance between elegant, abstract ideas and the cold, hard need for speed. Yeah, we want our programs to be beautiful and well-designed, but they also have to be fast enough to, actually do something.
And believe me, this is not just some theoretical game for academics. This research is fundamental to the tech that's all around us. We're talking about automated reasoning that powers AI. We're talking about verifying that the software running our banks, our power grids, our airplanes is actually correct and won't fail. It's about pushing the absolute limits of what computation can even achieve. And that leaves us with one last big thought to chew on. As the problems we try to solve with computers get harder and harder, and the stakes get higher and higher, which side is going to win? Are we going to lean towards perfect, provably correct elegance? Or will we have to choose raw, unfiltered efficiency just to get the job done? The answer to that question, well, it might just define the entire next chapter of computing.